Okay, so today we will start a new chapter called computer architecture. So for the computer architecture, previously we have already learned a lot of hardware stuff. So in general, the hardware stuff can be elementary logical gates like not and or XOR gate. And we have already learned arithmetic chips like half adder, full adder, ALU, so arithmetic logical unit. Then we learned sequential chips, so we do know how to do the RAM and how to do the counter. So usually the counter is used for program counter. So this one will control your instruction. And memory, of course, is for you to store the program. So now we want to combine them together to build our first computer. But there's a long debate there is what kind of computer, who will be the central for the computer. So whether you use the arithmetic logic to say that, okay, everything is just for computing. So you can see the old, before our modern computer, the old like in 16 or 1700, 17th century, they built a lot of computer. And this computer usually it's just the focus on the computer. So everything you write on whatever. So you program by yourself, but it cannot store. You just run these things, run the calculation. So use the ALU as the major part. And then for sequential chips, actually, we don't care too much. But today's modern computer, you will see that actually is not this style. And another thing for this computer is what kind of problem we can compute. So for example, can we compute for the weather forecast? Sometimes yes, sometimes no. Can we compute whether we can eliminate or whether we can forecast what happens in the future of the stock actually? This is for the data science, but before the data science, actually, we have no way to forecast. So the first question is what kind of problem we can compute? So this one is solved. This one is solved by Turing, and he built a mathematically way to say, okay, if you can compute, everything can be computed on the Turing machine. This Turing machine is the way to tell all of us what kind of problem can be computed, which you will learn in algorithm class. And then the other thing is Turing machine we cannot build very efficiently. So we need a very, very practical computer. And the practical computer actually want to do is we should make sure what kind of key concept we want to do. And then we have a very famous one called Von Neumann, John Von Neumann, and he gave the concept to say that the stored program concept. What it means that everything, no matter your data or your instructions, all those things are treated like binary and stored in the computer. And when you want to produce or you want to execute these things, all these things will be loaded to the arithmetic logical unit. And then it will compute and give the output, and this output will be stored back to the memory, or it will go to the output device. Furthermore, CPU will do another thing is try to figure out which one will be the next instruction so that it can produce. So the executing the current, so this one in the processing logic, we call it fetch execute circle. So fetch means you get this function and compute. And then you will compute some function and out equals to some function of some register values. And then write. So the next one after fetch, then you execute. And when you execute, when you finish execute, you will write the ALU output to selected registers. And then as a side effect of this computation, figure out which instruction to fetch and execute next. So in general, I will share the screen to see that today's computer so today's computer we will do is looks like this. In the middle is CPU. So this is a computational central process unit, include arithmetic logical gates, and as well as certain kind of registers and control. Then in the other parts, everything will store in the memory. So your data will store in the memory, plus your program will also store in the memory. So data plus program all stored in the memory. Or sometimes we call this program as an instruction. So you have already learned the physical representation, binary version of the physical code. So this is the program you will store in that. Oh, the CPU will fetch the data and the instruction from the memory and run it. When it finishes, it will store back to the memory. So of course, how do I enter? So another portion is we have certain kind of input device. So the input device will communicate with CPU. So for example, your keyboard is your input device. And now today we have many input devices. For example, you can have not only keyboard, but also you can have a mouse. You can also have certain kind of screen if you can write on the screen. So it's also the input device. So for the input device is this guy is only one direction. So the input device will goes to the CPU. Okay, so when you finish the calculation, you will do the second thing is when you finish your computation, you will do output device. So output device, CPU will write things to the output device. And this output device may, for example, as your screen is one output device, and another one output device, it can be other things. For example, your printer. So it can print out your document. So this one is also output device. So all these things you write from the input device or you write to the output device, all these things, the data will be stored in the memory. So you will see that actually memory will store all the data in the program. and the CPU will calculate and communicate with memory, communicate with input device and output device. So now this is today's network, today's modern computer. So what's the computer architecture this chapter will do? This chapter will first build, since memory store the data and the program is the most important part, so we will first build the memory. This memory not only store the data, but also for the instruction, and those data can be from the CPU, and it can also from the input device, and it can write to the output device. And then we will first build the memory. Memory design. So for the memory, the first thing we need to do is the instruction memory. We use our machine as an example, hack machine as one example. Okay, so for the instruction memory, we will build okay, so this is for instruction. We have RAM 32K. And we have input. This one is address. We have 15 bits for the address, and output will be 16 bits. Okay, so this one for the instruction. So instruction memory, the address, the input is address. This address is 15 bits, and the output will be 16 bits. So the RAM size, and we say that the instruction is stored in the RAM, read-only memory, and we don't write into the RAM. We only write at the first, and then we don't rewrite or instructions. We don't generate instruction when you run your code. So the RAM only have the address to fetch the instruction. The address is 15 bits. One question, why we only have 15 bits? So please write your answer on the chat board, chat, or you can directly talk to me. So please think why we only have 15 bits. And our RAM size is 32K, 32 kilobits. Anyone have the answer? Hey, anyone got the answer? Okay, let us see. What is 32K? And then what is the A instruction? Our A instruction is used to fetch is used to give the address of the instruction. Yeah, one thing is for A instruction is used to get the address, not tackle the get the address of the instruction. And the A instruction, we have 16-bit, and the leading bit is 0. So everything is leading bit is 0, and the 15-bit is useful for the instruction address. This is the first thing. And the second thing is for 32K. You can calculate 32K. Actually, 32K equals to 2 to the power 15. Right? 2 to the power 10 is 1K. 32 is 2 to the power 5. So 32K is the maximum. The address space will be 15. So consider the A instruction. This one is I need 15-bit. I totally only have 15 bits for different address. And then 32K for RAM is totally good, perfect things is 32K, the maximum, the number of bits it need to fetch each instruction is 2 to the power 15. So my address size will be 15. So far, so good? Okay, now you know that the RAM is viewed like this. It's quite straightforward. The function for RAM is just give me the address, then I give you 16-bit, and this is 6-bit out instruction. So this one is your physical code. So I give you 15 bits, your A instruction, I take the 15 bit because the leading bit is 0. So I just eliminate 0. So the next 15 bits is the address from the A instruction. Then I can get a 16 bit out is the C instruction or C instruction. So I can get the next instruction. Okay, so this is for instruction part. Now we look at the memory. So not only for the instruction, right? We say this is not only for the instruction, we also need to build for the data. So this is data memory. So of course, we still for our hack machine. Data memory is a little bit complicated because compared to the instruction memory, data memory, you need not only read from the data memory, but also you try to write into the data memory. So for data memory, we build 16K for data memory. We not only have the address, 15 bits for address, but also we have the input. We can have input. So input in is 16 bits. Okay, so this is the RAM. And the RAM, I only have 16K. So anyone have the problem? Why not? It's the 32K. Anyone have this problem? So if you have this problem, then we will look at when we continue build this one. But the thing is our A instruction is always 16-bit and 15-bit is used for address. Our A instruction always this length. So for our RAM only have 16K, but we will do address is still 15 bits. But the remaining one, so I have only 16K for the RAM for the data memory. What the other part we will look at in the future, in the near future. So it's a quite, I think this class can cover. So for the data memory, we have for data memory, we have two functions. One is write, one is read. So for the read function, and what we want to do is, okay, we should set address to certain kind of value k. This k is provided by A instruction. Right, so this is a read and set. So from read, you will do, so this is the first, you will set address provided by A instruction, and two, probe out. Okay, so you will read and the output will be the data. Okay, then the next function. So the next function we call the write function. So the read function actually same as the instruction memory. You set address and then probe out from the RAM. And the write is it's new. So it will first set address to K. This one is provided by A instruction. Then second, you will set in your input to X. This is the value. This is also, so you may store in the D register, or so this one may be provided by C instruction through D register, right? Through D register, you can store your data X and set it as your input, and you can store in any place. So usually you will store in the D register, and then we will set, so we will allow load to be true. Still remember our memory when we do the DFF? So we have the load bit. So the load bit to be true means you can load to the memory and run the clock. Right, so this is right, it's a little bit complicated. So actually there's 3 steps. So the first two is preparation. So you set address, this is your memory address you want to store the data. And then the next one, you set the value you want to store. Then the third step actually is we discussed in our sequential logic. So you should let load to be true, means you allow it to write to the register, write to the memory, and then you should run the clock, right? The clock should run so that it can store the data. Okay, so this is the second. So this is the hardware you will do, is the memory design. Okay, this one is not the finish. Actually, we have third things for the memory is we call the screen. So we need to do screen. Remember, this is the input, right? This is the input device. Your input device, your output device, actually. This is the output device. Output device for screen is actually you should put values stored in the memory, and then it will show on the screen. So this portion, we need to redraw this one. Our screen. So this is our screen looks like. Screen. This is the screen memory. So actually it's called screen memory. Screen memory, actually the output will go to the actual screen. So do I have the screen? Can I draw a screen? Maybe this one. No, it looks like this. Okay, the screen. Okay, this is the flag in our hack machine. In our hack machine. In our hack machine, we have a screen. So for the screen, the first one, we need to know that what is the screen resolution. So the screen resolution will be 256 times 512. So black and white. So black and white. So this is the screen. So the screen size is actually we will do is store. Actually, this hack machine has this screen. So since it's black and white, actually we just need a 0 and a 1 to represent for each bit. So we use the bitmap screen to represent black and white. You can use 0 for black, 1 for white. So this one is quite easy. And totally how much we need is 256 times 512. So let us see how big the memory we need. So 256, actually you can treat So 1024 is 2 to the power 10. So this is 2 to the power 8, 2 to the power 8. Right, so this one is 2 to the power 8. And then 512 equals to 2 to the power 9. So this is a bit. This is bits. So the total bits we need is we need are 2 to the power 17 bits. Okay, then every 8 bit is 1 byte, so is 2 to the power 14 bytes we need. So this is the bytes we need. So is actually we need is 64 kilobytes, kilobytes. Okay, so still remember our storage for our memory. So each output will be 16 bits, 2 to the power 4. So this one is the output is 2 to the power 4. So actually one line here will be 16. So, but the bytes is 64 kilobytes. So the address is 15, so I can cover. 14 is okay, so I can cover. Oh, this is the screen. And the screen show looks like this. I can copy to see that. So you can look at how do we analyze this screen. So each one, so the row I have one. So how do I organize my data? Okay, so for the screen memory, how do I organize my data? So my organization will be here. So I have 152 bits per row. And you can see that my output of the screen memory, my output screen memory will be 16 bits. So my output bits is 16 bits per row. Per output, if I read once, I get 16 bits. So 152 equals to 16 bits times 32, right? So this is power 4. This is a power 5, so totally will be power 9. So this one is 16 times 32. So what does it mean? Each row will be stored through 32 rows in the screen memory. Okay, so this one is the way we organize. So for example, row 0, I will store is from the address from 0 to 31, right? So this one is my first row. I use 32 rows in the screen memory to represent one row on the screen. And then row 1, I can address from 32 to 63. Okay, so this one is our row 2, row 1, the second row. Okay, we can continue this work until row 256. So this one will be start. Oh, okay, no, not 26, 25, because you start from row 0. So if you start from row 0, it looks like this. So row 25 is address is from 8129 to 8160. So this is the last row. So the last row on the screen. And then the bit will be, so this one is for the screen memory. Oh, this is screen memory. And the last one for the screen memory. Any questions? Any question? Okay, great. So we're almost done. So this screen memory actually is 64 kilobytes, right? So this one, okay, I can erase this part and we need another thing. Okay, this is memory design. And the last one we still need to keep in the memory is keyboard memory. Okay, for hack machine. So we do the standard machine, standard keyboard. So standard keyboard. So standard keyboard, you will have uppercase letter, lowercase letter, and keyboard. Okay, so for this one, I change it to here. So the keyboard. Okay, so the keyboard actually you only have input, no output. No, output will go to the memory, right? To the output. So output is the value of this keyboard. This is the keyboard. So there's no address things. So we have just the keyboard. So your traditional keyboard. Select. This is keyboard. Memory. So you go to the memory. If you want to know which key you hit, is just one single 16-bit register is only need a single 16-bit memory. Okay, 16-bit memory. When you keep, if your key is pressed. So we have certain things need to deal with the keyboard. The first thing is we should have the scan code of the currently pressed key. Okay, so everyone knows ask2. ASK2 number. So small a for 65, big A, no, A is 65 and uppercase A is 97, so something like that. Okay, if you know ASK2, then it's okay, great. So our keyboard, so we will use ASK2 to do this. And we have some special case, special number for special characters. So for example, the new line is 128 and is 135. So F1 to F12 is 151 to 141 to 152. And the home key is 134. So this one is the special keys. We have backspace, left, up, right, down, special keys. All is included in our keyboard memory. Okay, so memory, since this one is just a 16-bit, one 16-bit keyboard, so I only need actually one address for that. That is good enough. So now, this is finish our memory. So now, we will look at, actually this one will keep together. So we go back to our first question is why our data memory, our RAM memory only have 64 kilobytes, not the like the instruction memory have 32 kilobytes. So as the last question in this class, so this one I will draw the whole picture of our memory. So our memory will have two parts. One is the ROM 32K. So this is everything is for instruction. And you will only have address to input, no 15 bits. Okay, so okay, and the output is the instruction. So out 16 bits. Okay, so this is the first part of our memory. It's called RAM. It's only for instruction. So I should say this one is instruction only. Okay, now we have the second part of our memory. Is RAM. This is for data. We have 16 kilobytes for the RAM. And this one actually is not itself. So below it, the whole memory, it will have the first part is the RAM 16K. And then after that, Below that, this RAM 16K, below that is the screen memory. We call the screen memory map. Okay, upper is the RAM 16K, then the lower is the screen memory. And below, we also have the keyboard map. Okay. Oh, the whole memory is, sorry, so should not draw like this. Maybe I can do this way. So screen. And then after that, you have one more thing, is the keyboard. Keyboard. Okay, so the whole data memory divides to three parts. One is the RAM, one is screen memory map, and the other one is the keyboard map. Why we call the map? Because you get the information and map into the memory. So you should store the information. So this one we call the map. So this thing, I still have address is 15 bits, and you have the input data 16 bits, and the output data is 40. Okay, so this one is we have the address 15 bits. Okay, don't forget we have, okay, I don't draw anymore. I don't have time. So for the data memory, actually you partition into three parts. RAM data for the data itself running for the instruction, so it's the RAM 16K store the data. Screen memory map is deal with the output device screen, and the keyboard map deal with the input the device from the keyboard. That's why when you look at RAM, it only have 16 bits, 16 kilobytes. Compared to the ROM, you have 32 kilobytes. Okay. So that's all for today's class. Any questions, you can type in the chat room. If not, see you on Wednesday.